Hello, so let's make a start. Good afternoon. Thanks for joining us for the last session of the day here. My name is Michael Weibrow. I'm from Monash University. And it's a pleasure today to be chairing this CG&A invited partnership presentation. And the session title is Visualization in the Industry. And this session today is the first of 3 such sessions at the conference, which feature invited presentations from selected papers from the Computer Graphics and Applications magazine. So IEEE CG&A features a mix of curated magazine-style educational and opinion pieces, and also a core of peer-reviewed research articles. And the presentations in this session and the following 2, which are tomorrow afternoon, are this later kind of peer-reviewed articles. So we have 6 presentations today. We'll be using Slido and for questions, and this will be in the Mistletoe section of Slido, so you can put your questions there. And the first of our presentations is a remote presentation, and this is a talk entitled Surgical Navigation System for Low Dose Rate Brachytherapy Based on Mixed Reality. And Ziyang Zhao from Southwest University in China will be giving this presentation. Thank you.
Good morning, everyone. Today, my presentation is about a surgical navigation system for low-dose rate brachytherapy based on mixed reality. The reporter name is Ziyang Zhou, and it is come from the School of Mechanical Engineering, Tianjin University. The presentation of today is about the 2 parts. First is the surgical navigation for brachytherapy based on mixed reality, and the second part is the overview of our research team. First, let me introduce the surgical navigation for brachytherapy based on mixed reality. We have developed a mixed reality guided brachytherapy system, and the phantom experiment and the animal experiment were performed in the Sun Yat-sen University Cancer Hospital, Guangdong, in China, to validate the accuracy and the effectiveness of this system. This is the pictures of the phantom experiments. The second part is the registration method. We use an electromagnetic tracker as a particle registration tools and track the surgical tools in real time. A novel hand-eye calibration method was proposed to achieve the transformation from HoloLens to electromagnetic tracker, as shown in the figure below. The ICP method was used to achieve the transformation from the preoperative medical images coordinate to patient coordinate. After we obtained the CT images from the CT scanner, we reconstructed the skin surface from the CT images and achieved the position of the fiducial markers. Together, we used the puncture needle to pick the same fiducial markers in the coordinate of the electromagnetic trackers, and then achieved the transformation from the EM tracker to the CT medical coordinate, and the hand-eye calibration method was used to calibrate the transformation from the EM tracker to the HoloLens tracker, as shown in the figure below. Phantom experiments were performed in 2019 in Guangdong province in China. The whole workflow of the real experiment is shown below. We prepared a phantom to simulate real patient with with dose planning and fusion all data into a phantom. After the phantom experiment is done, with our automatic needle and seed detection system, we can estimate the error of the needle and seed. Automatically, we will achieve a DVH comparison with the planning DVH to evaluate the effectiveness of the surgery. This figure shows the process of the phantom experiment. As shown in this figure, we can align the virtual medical images and the real patient together to help surgeons observe the condition of the patient at any directions. The figure 2 shows the surgical tools tracking in real time. The green needle is the preoperative planning needle, and the blue needle is the needle that tracked by electromagnetic tracker. Surgeons can easily perform insertion surgery with the agent, the green needle, and the blue needle together. And the figure 3 shows the surgeons wearing the mixed reality device to perform the surgery, and the figure 4 shows the post-operative medical imaging scanned by CT scanner to verify the accuracy and the angle error of the phantom experiments. Next is the experiments of the animal. Animal experiments were performed in animal operating room in Sun Yat-sen University Cancer Center in Guangdong Province. First, we scanned the pig and export the medical images, and the surgeons completed the pre-operative dose planning with our treatment planning system to show the DVH before surgery. And the step 3 is the mixed reality surgical navigation system. We automatically update the database and record the date, and then surgeon perform the registration and calibrate the puncture needle. As shown in the figure below, figure 1 shows the piggy in the CT scanner, and figure 2 shows the registration process, and figure 3 indicated that the pre-operative scanner of the pig, and the figure 4 indicated that the post-verification of the pig, of the insertion experiment of the pig. And this is the video in our laboratory to indicate that all the functions of this mixed reality navigation system with a phantom. You can see that the interaction module of this mixed reality navigation system is the hand gesture. We can use the hand gesture to drag the medical images to show the medical images at any directions. And we use the virtual buttons to control all the things in this mixed reality surgical navigation systems. And this one is show or hide the skin and show or hide the bone. You can see that the virtual skin and the virtual bones were aligned with the real phantom, and this is the show or hide the long module. And the skin, we hide the skin and the bones to show clearly of the virtual organs. And this is the forward play of the medical images. This system can automatically play the medical images from the first to the end and the end to the first, for bringing surgeons a more directly understand of the condition of the patient. Alright, this is the video of the surgical navigation system. Next, let me introduce our university to you. We come from the Tianjin University. It's the first university in modern China and founded in the 1895, Peiyang University in Qing Dynasty, and it is one of the first 16 national key universities since 1959 and the first 985 project units in 1998. We have 19 academic schools and more than 30,000 students and have 14,000 facility and staffs. Next is the introduction of our research team. Our research team comes from the School of Mechanical Engineering in Tianjin University. We have more than 13 PhD students and the master student, and this is my supervisor, Professor Yang Zhiyong, and this is my another supervisor, Professor Shan Jiang, and this is our student visits the Johns Hopkins University. Our lab have a great cooperation with the Johns Hopkins University and the Stanford University with Cardiff University, also including the including the famous hospital in China. And this is the presentation of this. This is the presentation of today, and thank you for your interest in your work. We are looking forward to further cooperation and research. And we thanks for the great support of the School of Mechanical Engineering, Tianjin University, and we thanks for the great support of the Sun Yat-sen University Cancer Center, Guangdong, China.
Okay, thanks. Thanks, Zayang. Can we bring up the Zoom, please? Just check. Oh, we don't have our speaker. Okay, I guess we could check and see later if they're here. So, I mean, if you do have any questions, maybe just annotate them with like first presentation and we'll collect them on Slido and we can ask later if the speaker turns up. Okay, Motaz, yeah, please feel free to come up. So our next presentation is on visualization for architecture, engineering and construction, shaping the future of our built world. And the speaker is Motaz Abdilal from the University of Stuttgart, Germany. We'll give him a moment to set up. And just a reminder for the other people who've joined us since we started, we're in the mistletoe room and you can put your questions on Slido. Thanks. Okay, thanks, Motaz.
All right. Hello, everyone. In this talk, I'm presenting on behalf of a relatively large team of architects and visualization researchers. In this presentation, I'm going to report on our experience working with architects and discuss visualization opportunities that we could identify in the engineering, architecture, and construction domain. So architecture is a habitat of mankind, and it does not only has ecological and economical relevance to our lives, but also social and cultural. A study in 2001 already showed that humans nearly spend 87% of their lives living inside buildings. In this context, the UN, United Nations, predicted that by 2050, housing and infrastructure need to be built for around 2.5 billion people. However, there are rising concerns in whether or not the AEC industry would be able to meet such a demand, given the decreasing productivity in the last 3 decades, especially when put in comparison with other industries such as the automotive industry. Additionally, the current practices and methods employed by the AEC industry are a significant contributor to climate change, accounting for over 40% of global energy use, 50% of the global waste, and 30% of the global greenhouse gases. So, in our project, working together with architects from University of Stuttgart, Germany, they identify 3 main solution strategies in order to tackle those challenges. And these strategies are researching new building materials. In this sense, they are experimenting with carbon fiber materials and buga or wood materials. And using these materials, they were able to come up with pavilions that you see on the slides. However, they are asking the questions: can we build more than just pavilions using these materials? but they are lacking for a digital tool to support them for identifying the structural properties of this material, evaluating their aesthetic criteria. In other words, one could say that the design space or the parameter of the design space are not clear for them yet. The second solution strategy is reducing the consumption of the building materials. And here it's a common issue in the AEC sector, over-consuming materials when building certain structures to account for peak loads that rarely occur during the lifetime of a building. However, this reflects the lacking of digital tools to support the practitioner in analyzing and monitoring the building under different circumstances, under varying topologies or materials. The third solution strategy is the use of cyber-physical systems, or in other words, the use of robotic fabrication. And this strategy aims to increase the productivity of the fabrication and the construction workflows. And on the slide, we see an example of progress already done. So we see an example of a transportable robotic fabrication unit that allow the workers and fabricators to assemble the structure on site, and therefore avoiding transportation and operational costs. However, it was obvious for the AEC practitioner that some of the fabrication tasks are better done by humans than by robots or machines. And then it raises the questions, how could we, for them, how could they coordinate this fabrication effort between a human and robot, especially when these share the same environment. In our research, or in our paper, we argue that data visualization could fill this gap and help in the digital transformation of the AEC industry into a more data-driven domain. And our arguments stem from three reasons. The first one is the inherent need of human judgment in the whole process. And this is not only true during the design phase, where the process has sort of creative and artistic sense, but also during the fabrication phase, as we said, where some tasks could be better done by humans than by robots. The second reason is the lack of standardization and the lack of data. And this is true. And lack of data, we mean in a digital format, especially true in the fabrication and the construction phases. And the lack of standardization, also true, as every building comes with a set of boundary condition and local regulation that cannot be easily transferred to another project. And the third reason is a breadth of domain involved in building such materials. So it's not only architecture, but also engineering, material science, robotic, computer science, social science. So there's many domains involved in such process. Therefore, when one thinking about how could we transform the industry into more digital-driven format, it would be hard to think of automatic solutions, given such as machine learning, for example, given the need for a human in the loop, and also the lack of data and the ill-defined tasks. In our work, we presented 3 different use cases. And in these use cases, we tried to identify areas where visualization research could contribute. For example, on the design phase, visual analytic systems could help domain experts coming up with better definition of boundary conditions, and especially for fiber-based structures. When thinking about collaborative fabrication between a human and robots, we showed an example of augmented reality-based solution. And similarly, we showed an example of situated visualization to show the status of a building after the completion of the whole process and how the building evolved over time. For more details, I would refer to the paper for the implementation and the prototypes. While we argue for visualization, but still, this is not a trivial task to design those visualization solutions. So in the paper, we discussed several of those challenges, and I'm gonna just maybe briefly discuss a couple of them here. If we talk about the AEC ecosystem, we have to think about this limitation of technology, especially during the design phase, where any tool we need to build has to fit with the already existing tools that are used by the EUC industry. We're talking about flexibility and the customizability. This is a known issue, especially in the field of software engineering, for example, and it stems from the fact that it's a co-design or many domains involved. So any solution we need to build have to target multiple users and have to address several analysis tasks and several level of abstractions. So to summarize our research, we argue for visualization as a vehicle to transform the AEC sector into more digital format. This transformation comes with a set of challenges. And thirdly, and interestingly, not only from our experience, while in this presentation it seems like visualization is more serving the architecture domain, we found that actually visualization research could learn one or two things from the architecture domain as well, since both disciplines are design-based disciplines. And it's interesting also some of the ongoing discussion right now in the visualization community about the rigorous evaluation and how to come up with sort of quantifiable measure for evaluation. Similar discussion were already there in the architecture domain in the last century. With that, I'd like to end my talk. Thank you very much.
So while people put questions on Slido, I have a couple of questions, Motaz. You mentioned the cyber physical systems. How common are their use currently in this process?
Well, yeah, I mean, they use them at least in the research academia. It's been used at least with the people we collaborated with in University of Stuttgart, and like the two pictures that I showed with the Buga wood pavilion was already completed by using robotic arms. So I would say it's already proven to be functionable.
Okay, thanks. Wolfgang Agner asks, you mentioned the challenge of a variety of data. Mm-hmm. How do you deal with the need for connecting to application data or transforming it accordingly for your projects?
Okay, can you repeat the question again?
Yeah, you mentioned the challenge of a variety of data. How do you deal with the need for connecting to application data or transforming it accordingly for your projects?
Well, I assume like some sort of cloud-based solution could help addressing these challenges if two applications need to connect to each other with transforming the data. But I think one of the we spend like decent amount of time trying to come up sort of with a unified sort of schema for the data that could be used by different workflows. So coming from the design until the fabrication and construction. So coming up with this scheme is one step, and then putting up in a sort of a cloud where different parts could access it is, I would say, the should work.
Okay. And one further question. You mentioned a number of different challenges on towards the end of your presentation. How much have these been validated? There's obviously a number of stakeholders in this process. Have you sought feedback on these?
Well, some of these challenges is not new, I would say. So already you face them when you try to build a typical visual analytics system for other domains as well. But I would say what's different in the architecture domain is that they share this design aspect when they build or come up with this design, and they don't like a tool to tell them what to do. They like more to explore. So they don't like absolute truth or this is how you should do it. You just like maybe a recommendation, and then they can explore more. And the other thing is, I would say different than other domains such as biological domain or medicine domain. I would say, the breadth of domain involved in the whole thing. It's in architecture, it's more. So it's not only architecture, but also engineering and material sciences. So that all of them has to talk to each other. So it's kind of, when you try to build a tool, you're not only talking with architects, but you also have to talk with others. So it's making the, I would say, the requirement gathering elicitation phase of a software a bit lengthy, exhaustive. So that's also one of the things.
Okay. Let's thank Motaz. Okay. Sure. No problems. Sure. So while Vinny's setting up, our next speaker is Vinny Sejan Victor from the Fraunhofer Institute in Germany. And this presentation is Visual Parameter Space Analysis for Optimizing the Quality of Industrial Nonwovens.
Hi everyone, I'm Vinny Sarjan Victor. I'll be presenting a paper, Visual Parameter Space Analysis for Optimizing the Quality of Industrial Nonwovens. This is a collaborative work between the Fraunhofer Institute for Industrial Mathematics and the Technical University of Kaiserslautern. Industrial nonwovens are high-tech, engineered and innovative fabrics which are made from fibers. Due to their tensile strength and filtration properties, they are used in many applications, either with the combination of other materials or alone. The production of industrial nonwovens received higher attention from the general public during the COVID times due to the increase in demand for the technical textiles that are used for infection protection. So these nonwovens are produced using a process called spun-bond processes, where a molten polymer is extruded through thousands of filaments, and they're twirled around by air and they laid on a conveyor belt. The general goal of this process is to optimize the quality of these nonwovens by reducing the resources. So the quality of these nonwovens are affected by many process parameters that are involved in the manufacturing process. To find an optimal quality, we need to find an optimal combination of these process parameters. To do this, we need a systematic navigation through the space of these process parameters. But this process is difficult in an industrial setup due to its stochastic nature. So usually a digital twin is used to analyze this quality, where the quality of the nonwovens are analyzed using a digital image of a nonwoven, which replicates this physical process. But again, in this approach, this requires a lot of time to run the simulation using these digital twins. And also the optimization process is currently either done by trial and error or require domain expertise. So hence, we use machine learning model to map these process parameters to the product quality in real time. And then we use this machine learning model for doing visual parameter space analysis. So before moving into visual parameter space analysis, let us look into the process parameters and the product quality. We have 5 process parameters. Sigma 1 and Sigma 2 are the standard deviation of the nonwovens in machine direction and cross direction respectively. And we have noise level, which take into account of all the random effects that happens in the production of the nonwovens. This feature tells how deterministic or stochastic the nonwoven lays on a conveyor belt. And we also have number of spin positions and the belt spin ratio, which is the ratio of spinning speed and the belt speed. So the quality of the produced digital nonwoven is determined by coefficient of variation, which is a statistical measure for a relative dispersion in the data points. The lesser the CV value, the better is the homogeneity of the product, and hence the textile strength and the filtration properties. So now let us come back to visual parameter space and analysis. So the users of our tool involve people with different domain of expertise. So after a initial requirement and a phase with the users, we came up with 4 major requirements that needs to be fulfilled by our visualization tool. We need to provide real-time navigation through the entire space of process parameter, and we need to show analysis for understanding the influence of these parameters on the product quality, and we need to show the users lead the users visually to find an optimal combination of parameters that are robust to small parameter settings. And we also need to show the users different process behaviors of the production process, and need to eliminate them if any of the process behaviors are unfavorable to us. So visual parameter space analysis conceptual framework proposed by Michael Sedelmeier and colleagues forms the basis for our framework. So based on this framework, we propose Virtual Nonwoven Explorer, a first visualization tool for textile engineers for optimizing the quality of industrial nonwovens. So we have 4 tabs in our tool based on the requirements. The first tab is the parameter tuner. Here, the user can provide different parameter settings and store them as traces, and this helps the user in comparing different nonwovens based on their quality. So the main goal of this tab was giving the user interactive navigation through the entire parameter space to get an overview of the system. So to see the influence of different process parameters in the industrial product, we provided 3D surface plot where the user can select a combination of parameters whose effect he needs to be analyzed. Based on the selected parameters, we show a 3D surface plot that shows the change in the product quality by changing these 2 selected process parameters while keeping the other parameters fixed. So one of the main goal of this tab is the rapid identification of local minimas in bivariate settings. So in an industrial setup, sometimes a suboptimal non-sensitive setting is preferred than a optimal sensitive settings. This is because we cannot ascertain all the parameters to have the exact value because of the various errors involved in the production process. So hence we provided a sensitivity analysis for the user to find the sensitivity of the parameter settings. So this analysis consists of input space graph where we apply principal component analysis and reduce the space to 2, and we project the principal component 1 and 2 of the process parameter as a scatter plot, and output space where the corresponding predictions of these values are again reduced space using PCA, and they're plotted as a scatter plot on the first and second principal component. And we have the parallel plot to give the context of the process parameter settings which are selected, and we have the user input. So for the analysis, the user first selects the point of interest. We call this as focal point, around which he wants to see the changes, of which he wants to see the effects of how small changes around them affects on the product quality. So then he selects the number of process parameters around which he wants to see the changes and update the local neighborhood of this point. And then he updates the local neighborhood of these points. Then if you can see from this figure, he can see how a small changes around this selected parameter settings has changed in an output space graph. And also in the parallel plot. So using this analysis, we were able to find some of the parameter settings that are optimal but are sensitive to small parameter settings. If you can see, this red line is having a lower CV values, which is preferred according to our quality measure, but a small changes around them is causing a lot. It's very sensitive to small changes around them, considered the blue line. Sometimes the user might prefer the blue line because it's not that sensitive when compared to the red parameter settings. And additionally, to bring in target-oriented navigations, we also colored these points based on the clusters. We clustered the output space domain into different clusters, where each clusters represent a particular behavior in a production process, and we assigned a quality measures for them. And then these points are colored based on these clusters. And using this, it's easy to find when the process changes its behavior from one process to one behavior to another behavior. And if that behavior is not favorable according to our requirements, we can avoid this parameter settings. So to summarize, we showed how a combination of a digital twin, machine learning, and visual analytics can be successfully used to optimize the quality of industrial nonwovens. For this, we proposed a visualization tool, a virtual nonwoven explorer, that helps the textile engineers in finding optimal and robust parameter settings. This tool reduces the time and domain expertise required in that analysis. For future work, we are planning to extend human feedback into our analysis. If you can see these two figures have the same quality measure, but they look differently. So sometimes the aesthetics also matters in the production process, depending on the requirements. So we are planning to add these images in our analysis at the end for the user to choose based on the aesthetics of the material. So thank you.
Thanks, Vinny. Wolfgang Agner says, on your workflow slide, domain knowledge is mentioned as one component. Is this modeled digitally? If yes, what approach is used for knowledge modeling? Yeah, on your workflow slide, where you have domain knowledge. Lower left, where you have domain knowledge. Is this modeled digitally? And if yes, what approach is used for knowledge modeling?
This is, in our case, it's not modeled digitally. Here, domain knowledge, we got it from the industry experts who are involved in this process. And based on, we use this domain knowledge to get the parameter ranges, what parameter ranges are like physically make sense, and what are the parameters which are really important to take care of this. So it's more of like a discussion with the domain experts rather than taking it like digitally.
Thanks. And you talk about parameters as being sort of fixed throughout production. Does it ever make sense that parameters would be varied during production? Is that a thing that can happen?
If you can see the first two parameters, sigma 1 and sigma 2, these are like the stochastic parameters which are controlled by the process parameters, suppose like an airflow or how much. So these can be still varied a little bit that based on this one. But if you can see the spin positions, it's fixed during the, like you can change it during the design, but it's fixed when the machine is already done. So yeah.
And one final question. You talked on one of your requirements being unfavorable progress behaviors. How do you show those to the user or prevent them from selecting parameters that lead to them?
Okay, like we have like, I haven't shown in this slide because of the time thing. So we have like clustered this whole output outcomes, and we clustered it, and we found like a major 5 clusters, and we assign a quality measure to each of these clusters. Like based on the product quality, you can rate it like 1, 2, 3, 4, 5, like 1 being the least and 5 being the most, depending on the quality. So since you know these colors of these process behaviors, whenever you do the navigation, whenever in this slide, whenever the color changes, so you get to know that you're moving from one process behavior to the another one, so you can just move around there. So yeah.
Great. Let's thank Vinny again. Okay, our next speaker is Johanna Schmidt from VR Viz in Austria. And Johanna is talking about reflections on visualization research projects in the manufacturing industry.
Thank you very much for the introduction. Yeah, so our talk is on more, it's not about a specific technique, but really about our experiences in different research projects we conducted in the manufacturing industry. This is a CG&A invited talk. You can find the link to the paper up here. We have already seen in that session that data is a valuable resource in industry, but unfortunately sometimes also largely unused because people cannot really access it. And more companies try to conduct interactive visualization to make use of this data. And that's also what we've seen in our experience, because we work a lot with companies in application-oriented research, and we see that more and more projects are now conducted in the manufacturing sector to better understand process data and to better understand manufacturing processes. So we came together, 3 people. These are the three of us. It's Lena from Fraunhofer in Germany. It's me from the VIRWIS Research Center in Austria, and Wolfgang Eigner from the University of Applied Sciences in St. Pölten. So we have 2 Austrians here, 1 German, and we joined, and we wanted to better understand what we can learn from the industry projects that we conducted within the last years. And here are some impressions of these projects. So these are some results. So you will see that we were mainly working with visual analytics interfaces. We were creating multiple view dashboards in most cases, very complex visualizations also in most cases that was necessary because the data is also very complex and therefore you need complex interfaces. And some more examples here. For example, there's a project where Lena was involved. This was done by Fraunhofer together with some motor engineers. They were designing motors, and then they had different simulation models of these motors. And they wanted to find out what would be a good performance, what would be a good parameter setting for such an engine. And Lena, in that case, employed a parallel coordinates dashboard, basically, where they could explore the different parameters. Another example is from Wolfgang. They had a project together with a paper producing company where they had to analyze different types of data, also text and sensor data, and where the process engineers wanted to find out when and in which cases production might fail, and some web-based dashboards were created in this case. So in total, we had a look at 13 projects we conducted within the last 4 years, 2 different countries, Germany and Austria. And I will now give a summarization of what we found out, what are the commonalities among these projects, and also what are the lessons learned from working in industry-related projects. So here is a summary of the challenges that we faced. So we put together what were actually the main challenges that we encountered when starting the projects. And the large words you see here is data, of course, so data was involved all the time, but also large. So in all cases, the solution space was large and also the data was large. This is, of course, a main issue when creating visualizations for such big data sets. And these are the types of data that we were working with, and you can see a clear winner in so to say, which is time series. So very clearly, time series data was the main data type that we were working with. And this is also not surprising because these are projects from the manufacturing industry. And of course, they have a lot of sensor data, they have a lot of IoT data, so time series was very prominent here. On the other hand, we also had ensembles and we had AI models. So this is getting more and more important in the industry, that they have simulations, that they have models, and they would like to understand the different outputs and results. And then there are some outliers here like audio files, graphs, and spatiotemporal that occurred only in one project each. The users that we were working with were mostly engineers, and engineers with little to no experience in data analytics and data visualization. That makes it quite challenging to create a complex visualization, because the visualization literacy is not that high for these people. They know the processes very well, they know the data, kind of, or at least they have an idea how it looks like, but they're not really skilled in doing statistical analysis, doing data analysis, and looking at data visualization. And that was also the reason why, if you have a look again at the examples that I showed before, you might notice that in most of the cases, we employed basic visualization techniques. So that was in 9 of the 13 projects, we were just able to employ basic techniques like mostly scatter plots, line plots, bar charts, simply because these are the charts that engineers can read very easily and where they're not overwhelmed with the information. We had some projects where we were able to create more advanced visualizations. There is sonification here and VR, for example. And only in 2 projects it was necessary to really create a customized visualization. So in most of the cases we used basic techniques and we arranged them in a multiple view dashboard in most of the cases. And what did we learn from the project? So these are the 5 lessons learned that we agreed on and that occurred in almost all projects. So in the radar chart, you see the number of projects that where the lesson learned appeared, basically. And just doing around here. In all projects, so really in all 13 projects, not surprisingly, the success of the project depended on whether the partners were interested and committed to the project. So only if really the engineers, even though they are a little bit suspicious about data analytics, they at least need to be interested and committed to do such a project. Another interesting lesson learned was that it makes sense to involve the end users because they have a notion of how to visualize the data, what they want to see, and it helps to create a better result. That also relates to domain practices because there are some practices already in place when it comes to color maps or to certain charts, and it really makes sense to employ these practices. And the other 2, the last ones, they are quite interesting. So in all of the projects, it was absolutely necessary that the final result, that the solution fits into the existing technical environment. If that was not the case, it wouldn't have been used by the engineers. And also very interestingly, in 10 of the 13 projects, which started out as visualization projects, we actually ran into data problems because the data was not available from the beginning, or the data was scattered among different databases, and it was actually very hard to get the right data in the right quality at the right time. To compare with related work, some of these things are already known. So we can confirm that this interactive visualization gap still exists. We can also confirm that the design study methodology as published by Sedelmeier et al. Is really a great guideline for conducting such projects, and it also won the Test of Time award. That also shows the importance of this paper. And also the challenges of having the right data at the right moment was mentioned by Valny et al. But in our projects, we didn't find any other reference that really emphasizes the challenge for how to integrate such a project into the environment really from the beginning. So this is something that we found out is very, very important, but there's no real good guideline on how to do that. And also the efforts for data wrangling and this data interconnection with scattered data is often underestimated and is actually a huge part in such industry-related projects. And with that, I would like to thank you for your attention, point you to the paper again, and yeah, thanks.
You have time for a quick question or two. So you presented a number of challenges kind of in your word cloud there. I assume they were from the researcher perspective. So other than the ones you presented on your final slide about things like involvement and involvement of end users, have you found other challenges from the collaborations from the industry partner perspective, maybe on particulars of the visualizations, etc.?
Yeah, one is because of the limited visualization literacy, it takes some time to get used to complex visualizations. And in many cases, people do not have the time. So this is definitely a challenge to find a trade-off between not making it complex enough, but not too complex that it's still used. That's one thing. And the other thing is, that's more a human-related thing, because then the knowledge now exists in the head of the domain experts. And when it becomes externalized to becoming a data-driven approach, sometimes that's also scary for them, because it feels like that we would like to replace them, which is absolutely not true.
Thanks. Okay, let's thank our speaker again. Okay. The next speaker is Michael Becher from the University of Stuttgart, Germany. Reflections on visualization research projects. Oh no, that's the, I've somehow, you're the next one, sorry. Situated visual analysis and live monitoring for manufacturing. I might do a little song and dance number to fill some time here.
Okay, so thank you for the introduction. I'm Michael. I'll be giving you some insights into our approach for situated visual analysis and live monitoring for manufacturing. We had a moderately large team from people from University of Stuttgart, and we were also very happy to have our contact person at Bosch, our industry partner for this project, join us in writing this paper. So manufacturing has become increasingly automated nowadays, and the machines log large amounts of data about their current state and about critical events such as error or malfunctions. And for operators on the shop floor, this means that their tasks have shifted from manual work to monitoring the machines, and they only really need to react when something happens. So maybe to just give us a quick introduction to the scenario and our approach, let's watch a small video that we did, and I'll try to narrate it a little bit. So right now, operators mostly have to rely on their previous experience or whatever they learned during offline debugging sessions to know about frequent errors and how to fix them and where to find them. So they need to walk around, and the information they are given is mostly limited to what is shown on small status displays at individual machines. Often there's an end-on board installed at the factory, like a large screen at the roof of the factory, but they don't necessarily always see this information. So what we wanted to do is we give them an augmented reality headset and a tablet computer so that they have access to the data at all times. And they are guided to errors that take place so that they can move over and fix them. And yeah, they can check the tablet for detailed information on what might be the problem with this specific machine. And they have this virtual overlay in the HoloLens that shows them where to go next to maybe fix an even worse problem. And yeah, that's pretty much what it's supposed to be like. So let's briefly talk about related work. I don't think I need to talk about visual analytics in the manufacturing domain again after the previous talk, which gave a great overview. Then there's also, of course, augmented reality in the manufacturing domain, which mostly deals with repairing or maintenance for individual machines. And for an overview of current situated visualization research, I would point you in the direction of this paper by Bresser and colleagues. So how did we go about designing the visualizations for situated analysis in a manufacturing plant? We did a pretty traditional iterative design process where we sat down with our industry partners several times, trying to understand the scenario overall and identifying what are the requirements they have and what are the challenges that they face in their production line, and also understanding what is the available data for us and what are the key tasks for operators on the shop floor. So with our industry partner, we came up with these 4 critical tasks, which is monitoring, which is all about immediate identification of the events that take place, analysis, which is about identifying correlation in the data and finding out causalities. And then there's also prediction, which is about anticipating and preventing, ideally, faults in the future. And of course, maintenance, which is about taking appropriate countermeasures. But in this paper, we really just focused on monitoring and analysis as a first step. So the system we built is a link view system, which splits stuff about across 2 devices, which is a portable augmented reality head-mounted display that people could wear, and a tablet computer. And the data is synchronized in real time between these devices. And the reason we use 2 devices is to overcome the limitation of either device. So with the HoloLens, you have a hand-free device, which is great for the operators, but it has a really narrow field of view, and you really can't put a lot of virtual content on there without overloading it. And the tablet computer, on the other hand, it's great for giving dense information and the traditional touch-based interactions, but it's not hands-free. So we try to combine them to maybe overcome both of these issues. So let's take a look at the individual parts in more detail. So the visual monitoring is mainly on the augmented reality headset, and we give them this overlay of the production line, which basically highlights the individual process step in the line with the colored frames. And then we also place 3D arrow icons into the frames if there's an event taking place. And the other major element for our augmented reality view is a virtual compass element. So we wanted to do something which is intuitive also for users that are not used to more complex visualizations. And so this virtual compass floats in front of the operators at all times, and it shows little arrow icons that alert them about malfunctions that are taking place, and indicates also the location of the errors, and a very shortened error message is also floating there. And the other view, which is on the tablet, is the traditional visual analysis, which gives them 3 views. So we have a timeline view, which gives the events per machine on the y-axis, and over time on the x-axis, and this is, for example, great to see things like the correlating events, like you can see here highlighted in the blue frames, that we have errors that take place at the same time at different machines, or you can identify machines that have a higher frequency of errors overall, which, for example, this gray area over the x-axis. And then we have a detailed view, which basically just gives detailed information for individual error events, like the detailed error message. And we have a spatial layout view, which gives the operators an abstract map over the whole production line. And here again comes the data linking into place. They also get the user position as the small person walking around on the map. So let's briefly talk also about hardware and implementation. We used HoloLens, the first generation, for this project. We built a custom C++ DirectX 11 app. Actually, we initially started using a Unity game engine, but I ran into some disagreements with the engine, and we had quite some troubles getting various libraries to work with various versions of the Unity engine. So we at some point just wrote our own software. And on the tablet, we are running a C# Windows Presentation Foundation application. And one of the implementation challenges was actually communication on the shop floor. So the machines, they report the events to a Microsoft SQL database, and we then scan these events and filter them for the ones that are interesting for us. And these get then sent via Wi-Fi to the companion app, and from the companion app, they are forwarded using Bluetooth to the HoloLens. And the reason we did it like this is that setting up a Wi-Fi connection on the HoloLens is very tedious, especially the first generation model. And also the Wi-Fi coverage on the shop floor is not always ideal. And if it gets lost, then at the very least, you still have the connection between the tablet and the HoloLens so that you can use the historical data stored on the tablet. And another reoccurring theme with augmented reality is scene alignment, which is always a bit of a problem. And we went with a very traditional approach here. And we used Aruko markers that we placed all over the shop floor. And once we recognized at least 3 markers, we could do a least squares fitting to align the real world and the virtual world. Right, so of course we wanted to gather a little bit of user feedback, and we did a first feedback round mostly to just get qualitative feedback on acceptance and usability of the prototype from real users. So we had 4 experts, and they all spent about 15 minutes each with the prototype, but they actually used it in a live production environment. So the production line was actually running and producing parts. We had 2 actual operators that worked in the production line and 2 members of the Industry 4.0 research group. We gathered feedback using free text questions, and we also did a system usability scale. And so what they gave us as feedback on the positive side is that they really liked the fast response time of our system to error events, which actually was a little bit faster even than what was displayed on the existing displays of the factory. And they also really liked the navigational support provided to them by the compass. Then they also remarked that they liked that there was no occlusion in our AR view, that they could actually see process steps that were hidden behind other parts of the factory in the real world. And the hands-free usage when only using the HMD without the tablet was also praised. In opposition to that, the tablet itself was not praised. They said that the 10-inch tablet is simply still too large to carry around at all times. So we basically need to find either a replacement for the tablet overall, or maybe work out a better workflow for them on how to use a tablet. They also pointed out that there might be some potential depth occlusion issues if for example, look along a large production line and error icons start to overlap in space. And then maintenance is something that they really wanted to have that we didn't cover in the tool, so that they frequently complained about as well. So in conclusion, I think we showed that such a cross-device situated visualization technique for monitoring and analysis is a promising approach. It gives fast response to critical errors for on-site operators, and it grants the on-site operators access to the historical data of the production line. And we also evaluated in a live operation production line to basically find out the missing features and identify the shortcoming during test runs. And with this, I'm done, and I'm ready for questions. Thank you.
Thanks, Michael. Wolfgang Agner says, how do you link the visualization on the tablet and the head-mounted display? Is there content that is redundantly displayed on both devices but using different representations?
Right, so I think the error messages are, for example, displayed both on the tablet in the full length and a reduced version, and on the compass on the head-mounted display. That is one element. And then, of course, the position is, it is shown on the tablet, and well, they know where they are in the real world. So this is basically also a data linkage, but only an implicit one, I guess. And apart from that, there was not too many overlaps, no.
Thanks. Another question was, how customizable were individual user preferences, and did operators express a desire to tweak options themselves?
Right, that's a good question. At the stage of our prototype, there was nothing we did, and from my memory, they also did not express the wish to do it yet, but it's definitely something that's valuable for the future, to have like different sets of settings for different user groups, like for example in this case the on-site operators and the researchers from the Bosch research group. They have probably different interests in what exactly went wrong in a production line.
And just one final question, what do you see as the next steps, like if you wanted to take this further and put it into production and have it be used?
So using newer hardware, trying to figure out whether this dual system with the tablet and the HoloLens is something to use in the future, or whether it might be possible at some point to just go and put everything on the glasses. And then, of course, integrating stuff like the maintenance tasks and getting a more complete tool overall.
Great. Let's thank our speaker again. So the final presentation of this session is a remote one, and it's Vanessa Kretschmer from Leipzig University in Germany, and the presentation is stress visualization for interface optimization of a hybrid component using surface tensor splines.
Welcome to our talk about our CG&A paper with the title Stress Visualization for Interface Optimization of a Hybrid Component Using Surface Tensor Spines. My name is Vanessa Kretschmer and I'm happy to have you. To start, let us think about cars, trains, aircrafts, and vehicles in general. All of them are important to our daily life, yet consume an immense amount of energy. To be able to tackle the climate crisis, we need to reduce their consumption. One way is by reducing their weight, by replacing heavy materials while preserving sound structures, so things don't fall apart. This is basically the core idea of lightweight construction. Here, visualization can play an important role in supporting engineers find critical areas and obtaining knowledge about the states in a component. In our case, engineers wanted to connect metal with polymers. They created a metal insert and wanted to connect this to a carbon fiber reinforced polymer, in short CFRP. So here the CFRP represents an arbitrarily shaped surface. As bolt screws and rivets would introduce discontinuities in the endless fiber setup of the CFRP, they added a polymer coating over the metal insert. To finalize the connection, the setup was sealed by resin injection. It was previously shown that the polymer coat helped increase the connection quality as it prevents sudden jumps in material properties and sharp edges. To further optimize the setup, they wanted to form low transmission elements on the polymer layer to alter and optimize the stress distribution, shown here as little bumps on the yellow-colored coating. The distribution of such elements were already been analyzed, yet one open question remained unanswered. How should they be shaped to benefit the stress distribution? Well, you may know that symmetrical tensors of second order can be decomposed in a set of eigenvalues and related eigenvectors. Regarding these principal directions, we may all have the image of an ellipse where the radii are described by them in mind, similar to this picture here. Taking this idea to a component, a central question arose. Are elliptic-shaped elements aligned with dominant stress beneficial? To answer this question, our domain experts simulated the previously described component model. We then had to find a suitable visualization method to analyze the interface layer where the low transmission elements should be placed. So, to address the hypothesis, we need to analyze the stress tensor field on the interface layer. This includes observations of the stress distribution and possible changes of dominance and stress on a surface level. When looking into available research literature, we found that two of these requirements are already met by tensor spines, which is the hyperstreamlines variant with an emphasis on the signs and relations of all eigenvalues. This method was originally designed to be suitable for the stress tensor fields. Therefore, we wanted to utilize it. This three-dimensional method builds on tensor lines by creating a tube around the line representing the traced eigenvalue-eigenvector pair by the radius and the color. The tube is supplemented by two perpendicular-oriented surfaces that represent the remaining two eigenvalues and their eigenvectors. The coloring of the perpendicular surfaces indicates the sign of their represented eigenvalues and can be used to indicate a switch in the dominance of the stress. This means that the absolute value of a perpendicular eigenvalue gets bigger than the traced eigenvalue, for example. Unfortunately, applying this method to a surface is not straightforward, as clipping would occur due to the intersection of the perpendicular surfaces and the component interface layer. Shown here by a simplified example, having a perpendicular surface for a tensor line, when looking from above, a user could miss parts, here highlighted by red circles, that would indicate higher values than actually visible. A proper projection would be favorable. So here's what we did. In the paper, we described an algorithm that can be used to define surface tensor spines. Additionally, it is also possible to use this algorithm to display hyperstream lines on the surface or tensor lines on the surface with varying stroke sizes representing certain values. To achieve this, we found a computer graphics algorithm with the name stroke parametrization. The method was originally designed to enable sculpting and texture editing following a path often produced by tracing the mouse or a smart pen over a surface. It is based on exponential maps leading to a texture mapping considering geodesic distances for triangulated meshes. The original method, unfortunately, did not include a description for paths of varying stroke width, which would be necessary since stress values are changing along a path. You might argue that having a constant stroke could be used to define a texture for every tensor line, defining the finished look for surface tensor spines or hyperstream lines. But this would lead to a need of having multiple different textures with different dimensions considering different lengths of the underlying tensor lines. This would obviously lead to a bad memory footprint and resolution issues. We therefore developed an extension that can consider varying ready without introducing artifacts. For a detailed description of how to achieve this, please consult the paper as it's quite technical. To give you a brief summary, multiple post-processing steps are necessary to avoid errors and artifacts compared to passing the changing radii when calculating the stroke parametrization. Based on the extension of stroke parametrization, we provided the engineers with the surface tensor spines to visualize the stresses on the interface layer where the low transmission elements should be placed. The visualization did not indicate areas of exceeding thresholds and no change in stress dominance. So for the idea of placing elliptical shaped elements on the interface layer, they can simply align the bigger radius of the ellipses with the major eigenvector direction. But to quickly show you the difference in the visualization for areas of changing stress dominance, we included a second picture here, where the perpendicular values have been artificially doubled. Here, marked by red ellipse, the darker saturated areas indicate these areas. Now, for the creation and alignment of low transmission elements, they requested a checkerboard texture with equidistant squares that can be used as a transparent overlay picture in their modeling software. For that, we utilized the quad remeshing algorithm that creates a texture definition as an intermediate step that then can be used to create such a texture. Here, artifacts at the top result from highly isotropic areas in the stress tensor field. The guidance was then used to model and craft two component variants. First, a double lap joint variant, and secondly, a more advanced component as described in the beginning. While early results of the double lap joint could only prove that using low transmission elements in the first place is overall better than using none, shown by the plots here, the second experiment showed an increase in low transmission and damage behavior of elliptical shaped elements over round runs. To sum this work up, we provided a new approach for the visualization community that can be used for line-based methods on surfaces, while sharing insights for engineers of structural mechanics in terms of low transmission element placement for a hybrid component. We further want to highlight the usefulness of computer graphics algorithms that are not directly designed for visualization problems, since these are often well-defined visual solutions which help us eliminate discontinuities and artifacts in the visualization. Future directions could include the extension of the placement guidance, for example, offering a semi-automated tool suitable to the daily workflow of engineers. And speaking of the workflow, we would like to see our algorithm used in their common software, as accessibility and the use of advanced methods is one big problem of our community. For my final remarks, I want to thank you all for your attention.
And we have Vanessa. Thanks, Vanessa. I had a question which is, I like research like this that takes an approach from one field and applies it to another. It's always nice. How easy was it to find this computer graphics approach, and how did you go about that, and how much did you have to look before you found it?
I hope you can hear me. Luckily, one of the co-authors, Alan Rocha, was familiar with this work because his own works about decal maps had a similar approach as the preceding work of the stroke parametrization, where the stroke parametrization is actually also based on. So that's why it was quite quick. But if he wasn't in the team, I would say it would have taken a longer time for sure.
Thanks. Were there any other questions on Slido? I don't think so, right? No, okay. All right, please thank our speaker again. And I just wanted to advertise, there's 2 more of these CG&A sessions tomorrow afternoon, both of them in this room after lunch. So I'll just say thank you to our tech, Valentin, and our student volunteer, Prakesh, and all of the speakers, and have a good evening, everybody.